Hi, I wanted to go over some matrix operation basics with you. So with matrices, we can't necessarily perform all of our regular operations that we want to, but what we can do is we can add or subtract two matrices. We can perform scalar multiplication or matrix multiplication, so there's two kinds of multiplication occurring here. And we can also do what's called the transpose on a matrix. So before I show you all the formal definitions, I want to do some examples. So let's start with finding let's do A plus C first. Okay, so if I want to find the matrix A plus the matrix C, I'm going to add component-wise. So if I want to know what goes in this spot, I'm going to add what's in this spot of A with what's in this spot of C. So I would get 2, and I continue on in this fashion to get the row 1, column 2 entry. I get 6. I do 2 plus 4. To get the, I didn't even do that. To get the first row, third column, I'm going to do 3 plus 3, which is also 6. To get the entry right here, the second row, first column, I'm going to do second row, first column of A plus second column, second row, first column of C, and I get 4, and I continue on likewise. So what you'll notice is in order to perform this addition, I need to have entries in all the places in A where I have entries in all the places in C. So if I try to do A plus B, for example, I might start and get 1 plus 0 is 1, 2 plus 3 is 5, and then would I put something here? Would I not put something here? Because I have an entry in the first row, third column in A, but I have no third column in B. So because of this conundrum, we say that we can't do this. That A plus B is not possible because A and B are not the same size. So in order to add two matrices, they must have the same size. So let's write that down. To add two matrices, they must have the same size. Okay, and this is because we add them entry by entry, and if they don't have the same entries, then we're out of luck. So let's try the next one. Let's try A minus C. Well, when we have A minus C, we proceed much the same way as when we had A plus C. We subtract entry by entry. So in that way, we would get 0, -2, 0, 4, 4, 7 would be A minus C. So again, in order to subtract two matrices or find the difference between two matrices, they must have the same size. If they don't have the same size, we say it's undefined. All right, so next up is scalar multiplication. So scalar multiplication means that we're going to take some real number, let's just say we're going to take the number 5, and we're going to multiply it times the matrix A. So this number 5 is called the scalar. We're multiplying a scalar, or a real number in our case, because we're talking about real matrices, times the matrix A. And this means that I'm just going to take every entry in A and multiply it by 5. So I'm going to 5, 10, 15, 20, 25, 30. Or Or I could do -3 times b, and that would give me 0, -9, -3, 15. And I could also combine scalar multiplication and addition. And in this way, I could combine scalar multiplication and addition and get what's called a linear combination of matrices. So, for example, I could compute 5a plus c. And I know what 5a is, it's right here, and then I could add it to c, or I could just multiply in my head all the entries of a by 5 and add them to c. And so I would get 6, 14, 18, 20, 26, and 29. And that would be my linear combination of A and C. A linear combination simply means that we're adding a multiple, we're adding or subtracting multiples of something. So we're adding or subtracting multiples of matrices, so we call them linear combinations of matrices. Okay, so let's do another operation, and our operation this time is going to be a matrix multiplication. So the matrix multiplication that we're going to do right now is going to be B times C. So matrix multiplication, especially if you've never seen it before, feels a little uncomfortable at first, because your first inclination might be just to multiply entries. And while that might be a good first attempt, what we see, or in our uses of linear algebra, we find that that is not the best definition. So this one sounds funny, but it is actually motivated by real uses. So if I want to multiply two matrices, I'm going to get a new matrix. And my new matrix, if I want to say let's just say that in my new matrix, I want to find entry in the second column, or second row, and the first column. What I do is I look up here at my matrices, and I look at the second row of my first matrix, and that's right here, and I look at the first column of my second matrix. Remember, in linear algebra, row always comes first, then column. And I take those two and I match them together. So I do 1 times 1 plus -5 times 0. And that gives me 1. So the entry in the second row, first column of this product is going to be 1. Okay. So I only chose second row, first column to make it a little bit clear what, instead of just starting with the first row, first column. But we can do this for every entry, so let's try it. So we already said the second row, first column is 1, so let's get the rest of them. If I want the first row, first column, I'm going to take the first row of my first matrix times the first column of my second matrix, and I'm going to multiply them, so I'm going to get 0 times 1 plus 3 times 0 will be that entry. If I want the first row, second column, I'm going to get the first row of my first matrix and the second column of my second matrix and multiply them together. So I get 0 times 4 plus 3 times 1. And continuing on, first row, third column, I'm going to take 0 times 3 plus 3 times -1. And now I'm out of columns in my second matrix. So then I move on to the second row. I've already told you how to find the second row first column, but let's just go ahead and reiterate. I need the second row of my first matrix and the first column of my second matrix. So I get 1 times 1 plus negative 5 times 0. And I'll continue on. My second row, second column, I get the second row of the first matrix and the second column of the second matrix. So I get 1 times 4 plus negative 5 times 1. And lastly, I'll get the second column, second row, third column. So I get 1 times 3 plus negative 5 times negative 1. So in all, when I multiply these two, I get 0, 3, negative 3, 1, negative 1, 8. Okay. This one takes some practice. Please practice on your own. So, what can we learn? What has to be true in order to multiply matrices? Well, in order to multiply two matrices, I needed to have the same number of entries in the rows of the first matrix and the number of entries in the columns in the second matrix. So that means the number of entries in a row, that's exactly the same as the number of columns in the first matrix. So the number of columns in the matrix that comes first needs to equal, well, I need it to equal the number of entries in a column in the second matrix, which is exactly the number of rows in the second matrix. So I know I need those two things to be equal. And so that gives me another result. Okay. To multiply two matrices, let's say A is m by n and B is Q times R. The number of columns here needs to equal the number of rows in the second matrix, which means that n, which is the number of columns here, needs to equal Q. So in order to do A times B, if A is m by n and B is Q times R, then those two need to be equal. Okay, so we'll talk more about properties of multiplying matrices in the future.